Hi everyone. Today I'd like to talk to you about the 4 fours problem. It goes something like this. Taking the digit 4 exactly 4 times, which numbers can we make? So for example, 4 plus 4 plus 4 minus 4 equals 8. This uses the digit 4 exactly 4 times, nice and easy. Let's take another example. 4 times 4, let's say minus 4 minus 4, is also 8. Okay, so we can make 8 two different ways. How about 4 times 4 plus 4 plus 4 comes out as 24. 4 times 4 is 16, plus 4 is 20, plus 4 is 24. So yeah, these numbers are nice and easy to make, but are there any numbers that we can't make? And let's see how far we can get. So I understand if you want to pause the video and see if you can make every number from 1 to 10, every number from 1 to 100 even. But I'm going to jump right in and start going through a few examples. So let's start at the beginning and start with 0. 0 can be written as 4 minus 4 plus 4 minus 4, right? 1, 4 minus 4 plus, and now I'm going to introduce divide, 4 divided by 4, and I'm also introducing bracket notation. So far, we've used plus, minus, times, divide, open bracket, and close bracket. These are all standard mathematical notations, and so I'm going to allow it for the sake of this problem. Number 2 can be written as 4 divided by 4 plus 4 divided by 4. Note that we need to use the digit 4 exactly 4 times. So if we manage to create a number using 3 4s or even 2 4s, it's not allowed. You must make use of all 4 4s. Let's try for 3. 3 can be written as 4 plus 4 plus 4, all divided by 4. How about 4 itself? Well, we can do it like this. We can go 4 equals 4 plus, well, I'm going to do 2 brackets here. 4 minus 4, which is 0, times 4 like this. So this is 0 times anything is also 0 added on to 4. 5 can be done like this. 4 times 4, I'm going to put a bracket around that for clarity, plus 4 divided by 4. Let's work that out. 4 times 4 is 16, plus 4 is 20, divided by 4 is 5. 6, 4 plus 4 plus 4. 4 plus 4 is 8, divided by 4 is 2, add that on to 4 to give 6. 7 is really easy, it's just 4 plus 4, which is 8, minus 4 divided by 4. We've already done 8, but let's just do it again for ease. Is 4 plus 4 minus 4 plus 4 minus 4. That'll do. 9, let me just write that better. 9 is similar to 7, except we just add this on at the end. 4 plus 4 plus 4 divided by 4. So for 10, I'm going to introduce a new notation, which is going to be the square root symbol. The reason why I'm allowing square root is because it is standard mathematical notation and it doesn't make use of any other digit. Therefore, 10 can be written as 4 plus 4 plus 4, that's 3 4s, minus square root of 4. Square root of 4 is 2, so 4 plus 4 plus 4 minus 2 is 10. Now again for number 11, I'm going to arguably cheat, and this is maybe cheating, maybe this isn't, but I'm actually going to use the digit 4 exactly 4 times, not necessarily just the number 4. And therefore, I'm allowing the use of the number 44 as so long as that takes up 2 digits. So for example, 11 is 44 divided by the square root of 4, further divided by square root of 4. 44 divided by square root of 4, which is 2, gives us 22, divided by 2 again, gives us 11. Perhaps that's cheating, but I'm going to allow it. 12 gives us 44 plus 4 divided by 4. Yep, 44 plus 4 is 48, divided by 4 is 12. I'll be very interested to see if anybody manages to post in the comments a way of getting the number 11 or the number 12 without using 44 like this. However, I will actually come up with a generic solution later on in the video which will cover many numbers, which includes these. 13 is also very similar to 11, but not exactly the same, obviously. 13 is 44 divided by 4, giving us 11 straight away, plus root 4, giving us 13. 14, let me think about this one for a moment. Oh, it's actually not too bad. 4 plus 4 plus 4, which is 12, plus root 4, 14. 15 is similar to 13, except we just add 4 on at the end. So we have 44 divided by 4, which is 11, plus 4, 15. Now I'm going to skip ahead to 19, as this is the first example where I want to introduce a new notation, which is factorial, which I'm going to allow because it is standard, widely recognized notation. So if somebody sees this, they'll be able to know what that means without having to go and look it up. So I'm going to start off with 4 factorial, which, in case anyone doesn't know, 4 factorial equals 1 times 2 times 3 times 4, which equals 24. And in fact, n factorial for some integer n has to be, if I had a natural number n has to be a positive integer, equals 1 times 2 times 3 up to n. So therefore 19 is 4 factorial minus 4, which is 20, minus 4 divided by 4, giving us 19. I'm going to stop there. I'm going to see if anybody can get from 1 to 100, which would be very impressive using these symbols alone. But I am going to move on to see if there are any other numbers outside the integers we can get. So for example, do you reckon we can get pi? The classic number pi, which is of course a transcendental number. So let's see if we can work something out. Let's note that sine of pi over 2 equals 1. Standard GCSE trigonometry. And let's see if we can use this to calculate the number 4. I'm actually going to allow sine as one of our standard mathematical notations because it is not a number itself. It is not a digit representing a number, and it's widely recognized notation. So sine is fine. So sine pi over 2 equals 1, which implies, of course, that pi over 2 equals arc sine of 1. And I'm being very careful to write it as arc sine and not sine to the minus 1 of 1. Reason is sine of the minus 1 makes use of a minus 1, which of course is a digit representing a number. So I'm using this notation, which of course gives us pi equals 2 arc sine 1. And finally, pi equals root 4 arc sine, replace the 1 with, say, 4 divided by 4. Of course, in this case, I've only used 3/4, but now that we're allowing the square root, I can replace any 4 with the square root of 4 times 4, which is exactly 2 4s. So a single 4 can be replaced by 2. So now if I ever manage to construct anything with fewer than 4 4s, I can just replace one of them with 4 by 4, which adds an additional 1 in. So for completeness, this actually equals the square root of 4 times 4 times arc sine of 4 divided by 4. Nice and easy. So let's move on. Is there another number we can create? Let's say e. Let's have a go at e. So let's note that e to the natural log of 4 equals 4. Because the natural log, noting that the natural log of 4 equals log to the base e of 4. Natural log is very often written ln, a standard widely used mathematical notation, and so I'm going to allow it for the sake of this. Therefore, the next step would then be moving on from this is to get that e equals 4 to the 1 over natural log of 4. This is me raising both sides to the power of 1 over natural log of 4. And then we're almost done. We just simply then substitute this 1 for 4 divided by 4. E equals 4 to the power 4 divided by 4 over natural log of 4. I mean, this can also be written as 4 to the power of 4 over 4 log 4. Easy. E, done. So we've managed to get a whole bunch of the natural numbers, that is 0, 1, 2, 3, 4, 5, etc. We've managed to get pi, we've managed to get e, but I wonder if there's a general rule of being able to get all positive integers, and in fact all integers at all, because of course if we manage to get a positive integer, we can just put a minus sign in front of it and we've got the equivalent negative. So let's suppose we have some number n, which is let's go for an actual natural number. Let's go n plus, so it doesn't include 0 itself. Let's note that n equals log to the base 2 of 2 to the n. Really straightforward. And just raising both sides to the 2 to the power of it and then taking log to the base 2. So this is, knowing your logarithms, this is quite clear. And then I'm further going to apply the same rule again, so that n equals log to the base 2 of log to the base 2 of 2 to the 2 to the n. Applying the same logarithm rule again, we'll get this. This does look like I've actually just overcomplicated it. I've written n also in terms of n with a whole bunch of 2's in there. So at first glance this looks like I've made things more complicated, but just hear me out. This also implies that n equals minus log to the base 2 of log to the base 2 of 2 to the 2 to the minus n, right? All I've done is substitute minus n in here and then move the minus over to this side. However, let's note that 2 to the minus n equals 1 over 2 to the n, which equals 1/2 to the power n. Now that's really, really useful. Because also, say if n equals 3, 2 to the minus n therefore equals 1/2. Sorry, excuse me. Therefore equals one over 2 to the n. It's 2 to the minus 3, of course. So it equals 1 over 2 to the 3, which equals excuse me, I've made a mistake. So if n equals 3, 2 to the 2 to the minus 3, therefore equals 2 to the 1 over 2 to the 3, which equals 2 to the 1/2 cubed, which therefore equals, as you may know, raising to the power 1/2 is equivalent to the square root, which therefore equals the square root of the square root of the square root of 2. Fantastic. The reason why this is fantastic is that I've managed to take n out of this. So therefore 2 to the 2 to the minus n equals the square root of the square root of the square root dot 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 square root, where there's n of these, n times of 2. So 2 to the 2 to the minus n can be written just with n square roots and then a 2. Which is really, really good news for us, because it means we can get rid of this n here. Therefore, n equals minus log, using this equation again, of log 2 of square root of the square root of the square root of the square root n times of 2, sorry. Brilliant. Because although I've written n times here, that's only to just express this term, this part generically in terms of n. If we have a given n, let's say the number 19 that we calculated before, we simply just write out 19 square roots, therefore eliminating the need for this n here entirely. And finally, just to wrap things up, I can therefore write n is equal to minus log to the base root 4 of log to the base root 4 of square root, blah, 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 square root 4. I'm going to write n plus 1 times, because the inner one is the square root of 4, so I'm substituting for 2. Brilliant. If we're any positive integer n, we can simply substitute this formula, and it will, using just 3 4s in fact, will value it to our number n. But can we do even better again, and perhaps even attempt to make all rational numbers? Of course, going back to our previous sheet here, this only works for any positive integer, but then for minus n, we just take away this negative sign here. Is just plus more of the same. And then of course 0 itself, we know is 4 minus 4 plus 4 minus 4. So that's every single integer covered. But what about fractions? What about rational numbers? So let a over b be rational, meaning a and b are integers and b is not 0. Okay? That's what it means for a number to be rational. It can be written as one integer divided by another integer. And of course, the integer being divided by cannot be 0 itself. Therefore, a over b, let's note that this equals a times 4 factorial over b times 4 factorial. All I've done is multiply through by 4 factorial over 4 factorial, which is of course 1. So I haven't changed the number at all. And now what I'm going to do is I'm going to divide through by a to get 4 factorial over b times 4 factorial over a. All I've done is divide the top and the bottom of this by a. Now, this bottom number the denominator might not be an integer, because when we divide 4 factorial through by a, it might introduce a fractional component, and even when we multiply that by b, it might still be a fraction. So we need to see if we can force this denominator to be an integer, and then we can use the formula that we previously did for constructing integers to work it all out. So this also equals 4 factorial over b times 4 factorial over a. Again, this still might not be an integer, but it's much more likely for the denominator to be an integer, in this case, a whole number, because 4 factorial has considerably more factors than just 4 factorial. 4 factorial just has the factors 1, 2, 3, 4, plus 6 and stuff, some bigger than that, but it definitely has the factors 1, 2, 3, 4, whereas 4 factorial certainly has all the numbers from 1 up to 24 as a factor, because 4 factorial is 24. And as you know, by the definition of factorial, it is the product of all the numbers up to and including the number it's applied to. So, it is definitely certain that there is a number k, so there exists k large enough such that 4 factorial factorial, loads of factorials, k times has a as a factor. And therefore, 4 factorial factorial blah 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 factorial over a is an integer. And therefore, b times 4 factorial factorial over a, I'm going to write that times like that, is also an integer. In each of these cases, we have k of these. And therefore, this number here, which is an integer, can be expressed using our previous formula from the previous sheet for calculating n, which is an integer. And it can also be expressed using exactly 3 4s. So we still have one more 4 to spare. Brilliant, because we need one more 4 exactly. So we express this b times 4 factorial factorial k times over a, and we know that such a k exists. We just choose any k which is large. Therefore, we write this can be expressed using 3 4s. And so, as a side note, a over b can be expressed using exactly 4 4s. Done. So this has been quite an interesting adventure working through all this stuff, and I'm afraid I haven't managed to find a way of expressing even larger sets of numbers. We have managed to express infinitely many numbers, and in fact, yes, okay, there's still countably infinitely many, as there are only countably infinitely many rational numbers. But perhaps somebody can, in the chat, can come up with a solution to the algebraic numbers, or perhaps even bigger infinities, such as probably not the transcendental numbers, because there's only countably infinitely things you can write down on a sheet of paper, and therefore there's probably only countably infinitely many numbers you can express using 4 4s. However, I still think this is pretty good. Perhaps someone can come up with computable numbers, or constructible numbers, or something interesting like that. However, for now, thank you for watching.